Welcome to part 1 of the USB debugging video series. My name is Yang Yu, and I'm a program manager on the Windows USB team. In this first video, I'll introduce some of the innovative debugging tools that we've created to help diagnose USB issues in Windows 8. In this talk, I'll describe what the USB debugging tools that are available to diagnose USB device and driver issues. We'll go over some of the basic USB 3.0 driver architecture that will be great background for the following talks. And then we'll have a short recap. You'll leave with an understanding of the tools that are available for diagnosing USB issues, as well as the USB 3.0 core drivers that can be examined with our debugging tools. We've spent a lot of time thinking about how device and driver developers will use the debugging tools. We actually have a vested interest in developing great debugging tools, since these are the very tools that we use ourselves to debug and diagnose USB issues. In designing the debugging tools, we looked at a variety of common issues that come up during device driver development and support. And these include issues where the device comes up as an unknown device, which is typically an enumeration issue. Bug checks that happen during client-driver interaction, power transition issues which are often hard to diagnose, as well as performance issues or when a device is just hung. Diagnosing these issues really requires insights into the state of the USB controller and the device. In some cases, this also requires analyzing a record of the recent USB interactions, and the ability to focus out all the information to focus on a particular device or transfer. Today, this involves purchasing an expensive USB protocol analyzer device or an expensive suite of software to analyze the transfers that are going on. There's still very limited insight into the current state of the USB driver stack. We also recognize that location matters. Where the issue occurs will restrict what tools are available to you. When the issue occurs on-site, perhaps during development of the device, you have a variety of tools available, including kernel debugging tools and bus analyzers, which allows you to debug the issue hands-on. But when an issue occurs off-site, such as after you've shipped the product and a customer is calling your customer support, you have very limited options. You can request a crash dump from the user or capture and analyze some debugging logs. Diagnosing USB issues is going to be faster with Windows 8 and USB 3.0. We've invested in a number of tools that will help with debugging device issues. With our USB debugger extension, you'll be able to inspect the internal state of all the key data structures in the USB controller and find out what's going on with the device. You can see a log of the recent USB transactions with our debugging traces and determine what interactions led to an issue. So there's also tools available to record events that occur in the USB driver and analyze them at a later time. And this will include the full data payloads, which is a feature that users have often asked us for. So in addition to the debugging tools that we provide, you can supplement the debug traces by adding events in your own driver. So you can see side by side what events that your driver issued led to a problem in the core stack. In order to use these debugging tools effectively, you'll need an understanding of the key USB 3.0 drivers involved. The picture here shows the layering of the USB 3.0 drivers with respect to the hardware and other client drivers in the system. In Windows 8, we've introduced 3 new drivers for managing the USB 3.0 XHCI controller. They are the USB XHCI.sys driver, UCX, and the USB 3 hub driver. All 3 of these drivers are KMDF drivers. The USB XHCI driver is the driver for the controller, whose responsibility is to interface with the controller hardware. UCX is the extension driver whose responsibility it is to provide USB level abstraction and validation of the client requests going into the controller driver. Then the third component is the USB Hub 3 driver, whose responsibility is to enumerate hub and devices on the bus. The other two inbox drivers shown in red are the existing USB CCGP drivers and the WinUSB driver that are modified to leverage the new USB 3.0 features. The tools I mentioned previously can be used to analyze the activities going on in each of these drivers. I've introduced the new family of USB 3.0 debugging tools that will let you debug USB device and driver issues much more quickly. By using these tools, you can reduce your development and support costs by diagnosing USB driver issues faster with our kernel debug extension, troubleshoot USB devices more easily by looking at recent USB interactions with our tracing, and leverage USB domain knowledge. All of these tools provide insights into standard data structures, which means you can leverage your USB domain knowledge to reduce ramp-up time learning how to use these tools. For more information, watch Part 2 to learn more about the kernel debugging tools, and the Part 3 video, which will discuss event tracing and the tools available to analyze the traces. As always, you can visit our USB blog on MSDN for articles and information. So, thank you.
Hi, my name is Ilyas Yaqub. I am the development lead for USB. In this video, I'm going to talk about innovations in USB debugging, more specifically about kernel debug tools. To get an overview of all the USB debugging tools available on Windows 8, please watch the part 1 of this video series. In this video, I'll first give you an overview of core USB 3 drivers, key USB 3 data structures, introduce you to debugger extension commands, and show you how to examine the internal state of software and hardware using these commands. As you may already know, that USB 3 controllers implement the new host controller interface called XHCI. The XHCI controllers support all USB standards, so you can connect any USB device, full, high speed or super speed, to XHCI controller. I want to first give you a quick description of data structures used by the host controller and software stack, so you can learn how to examine these structures using debugger commands that I'm going to introduce later in this talk. This slide shows all the XHCI data structures and how they are related to each other. To understand this, let's first understand the two sets of numbers you see on these slides. There is 255 and then 31. 255 is the maximum number of devices supported by a single controller. 31 is the maximum number of endpoints each device can have. So let's now explore or try to understand each of the structures separately and then find out how they are related to each other. Points to another structure called device context, except the first one. The slot ID 0 is reserved for the host controller. Device context structure is managed by the host controller and is used to maintain device configuration and state information to system software. This structure contains slot context and one or more endpoint context. Before we talk about the details of endpoint context, let us first find out the use of command and event ring. The command ring is used by software to pass device and host controller related commands to the host controller, and the event ring is used by the host controller to pass events to software, such as when the host controller completes a command or transfer, it detects a device was plugged into a port. Event ring is the structure used by the controller to inform the driver that an action is completed. Just like the device context array, there is one doorbell register for each device. The first register in this array is used to indicate there is a pending command on the command ring, and subsequent registers are for each device. Through the register, software notifies the controller that it has a device or endpoint related work to perform by programming the corresponding context information into this register. Now let us take a simple example of device enumeration. When a device is plugged into the bus, the controller notifies the software by writing to the event ring port status, change event, and firing an interrupt. In response, the software writes an enable slot command to the command ring and rings the controller doorbell register. In response to that, the controller posts a completion event into the event ring with the slot ID. This slot ID is used as an index into the device context base array for storing device context pointer. Now let us understand the structures on the far right side of this slide. Each endpoint context contains one or more transfer rings. Transfer ring is used by software to schedule work items for a single USB endpoint. When a transfer request, namely URB, is received from a client driver, the endpoint context for the transfer is identified, and then the transfer is broken into one or more transfer descriptors, also known as TDs, depending on the transfer type. The TDs consists of one or more transfer request blocks, also known as TRBs. The TRBs are used to transfer a single physically contiguous block of data up to 64K between host and memory. So a transfer ring basically consists of an array of TRBs. Two pointers in the endpoint context, DQ and NQ pointers, are used to track where the new TRBs are being added by the software and where the TRBs are consumed by the hardware. Once system adds all the TRBs for the TD in the transfer ring, it writes to the doorbell register. This tells the host controller there is a pending work to be done. Once this work is complete, the host controller posts a transfer event on the event ring, which then software uses to complete the transfer request. Now that you understand the software and hardware architecture of USB 3 at a very high level, I am going to introduce our new debugger extension DLL called USB 3 KD.dll. This DLL will be shipped with the WDK and WinDBG package. It has a rich set of commands to view the internal state of all the three driver components in a user-friendly manner. When you are developing a driver for your device, knowing how to use these commands will make your developing and debugging experience fun. This slide shows all the debugger extension commands grouped by the components they interact with. So let me first introduce the hub commands. So on the top you see a command called USB tree. This is the pivotal command which, in addition to showing the topology of the USB devices, it provides pointers to all the other commands that you can use to inspect the state of the hub, device, and ports. The other commands listed there lets you inspect the state of hub, device, and port individually. When I get to the demo, I'll show you how to use these commands. Then the next set of commands that you see on the slide is for the controller extension. As I said earlier, UCX provides a layer of abstraction between hub and controller driver. It has its own representation of controller and endpoint and manages software state of these entities. You can inspect the internal control state of these entities by using the bang UCX commands. So we have one command for controller, one for device, and one for endpoint. The pivotal command again is the UCX controller list. That command will point out all the other commands that you can run to get more information. Let's look at the commands that are for inspecting the controller state and the controller software driver state. At the top there is a command called xhci dump all. This command dumps information about all the host controllers on the system, and it lists all the other commands that you can run to examine the various structures we just discussed earlier. The bang xhci capability displays the controller capabilities as described by the hardware capability registers. Bang xhci command ring lists all the command TRBs that are pending and completed by the hardware. Bang XHCI device slots dumps information about the slot, endpoint context, and transfer rings. Bang event ring lets you examine, lists all the command TRBs that are pending and completed. Bang XHCI registers lets you inspect the state of hardware registers. Bang XHCI resource usage shows the common buffer usage by the driver, and Bang XHCI TRB lets you dump the details of TRB in a human readable form. In addition to these, we have a couple of utility commands, or what we call miscellaneous commands. Among them are USBD status that lets you convert a status value into a text, and Bang URB shows the information of URB, so it can decode all the various functions and show all the information of the URB in a human readable form. So let's now do a quick demo to see the output of all these debugger commands. I have here a kernel debugger, and it's loaded up a dump file from my test machine, and the first thing I'm going to do is set the symbol path. It's currently set to a symbols folder on my E drive. Then I'm going to load the new debugger extension that will be available with the WDK. It's called USB3kd.dll. Okay, the debugger extension DLL is loaded. Then the first thing you can do is type bang help to see all the debugger commands that are supported. So here you can see a long list here. They're all shown in an alphabetical order. Let's first look at all the commands for the hub. So the very first one, or the main command that you should run when you run into any problem, is the bang USB tree. Now this command shows you a lot of output. At the top it shows you the topology of the USB tree. So you can see there is a root hub, and then it shows you all the ports, and then if there are other hubs connected to it, then it will show the ports of those hubs in a tree form, right? Then the next list of group of information that you see is about all the devices that are connected to this controller or to this system, and then we'll see a list of hubs that are present. So there's a root hub and there's one downstream hub on this system. Now as you can see here, all the commands that are useful or that you could run, they all have DML linked to it. So all you need to do is just click on it. So let's first look at more about the hub. So I'm going to click on the root hub here, and there it gave me a ton of information about the root hub. At the top you can see here what are the capabilities of the hub and what's the current state of the hub. Then it shows you how many ports are there, how many 3.0 ports and how many 2.0 ports are there on the root hub. There are some descriptors that you can run or you can examine, and then it shows you the number of ports and a corresponding a command that you can use to get more information about the port. But what you see here is a high level summary of the port, which is what is the current state of the port, what are the last events that are processed on this port, and then following that is a long state history of the port. So as you may have heard in the previous talks that hub has 3 massive state machines to manage the state of port, device and hub as a whole. And what you're seeing is the state history of the hub as a device. So the way you read this state history is it's actually listed in a chronological order. So whatever the events that happen are at the top, and the event and the new state that hub has moved into, that's what is shown, and it's pretty much everything is in all the states are in very descriptive. So by reading through you can make a sense of what's happening even without the actual state machine diagrams. Okay, so let's scroll back up to the Bang hub tree and look at click on a device info, and here's the output of Bang device info. You can see here at the top it kind of shows you a summary of what the state of the device is, the product ID, the device description, the WITPID information, if there are any requests pending in the controller, then again all the device state history of the state machine, and then the device event history. I'm going to scroll back up to the USB tree and click on the third command, which is port info, and the output of port info is very similar. It gives you more information about the port, the number of the port, what is the current state, what events have been processed, all the history of the state transition that port has gone through, and the event history. Okay, so next let's look at some commands for dumping information about UCX. So the pivotal command here for UCX is UCX controller list, and here it shows you that the system has one controller, and then a hub has its own endpoints, and then there's a whole bunch of devices connected to this hub, and here are the information about the device and the endpoints each device has. So again, this shows you the entire all the information in a tree form, and then it also points out all the commands that you can run or you can click on to view more information. So I'm going to just click on one of the endpoints to see the state history and the event history of an endpoint. Now let's look at the third group of commands. This is for examining the host controller, and the pivotal command for the host controller is xhci dump all. It does not take any parameter, you just do bang xhci dump all, and it will find the controller on the system, and it will give you a summary of information about the controller. So here you can see I have a Renesas PCI controller on my machine, and then here are all the commands that I can run to get more information about the controller. So I'm just going to click on a couple of commands here. So let's click on the xhci capability, and this one shows you all the capabilities of the controller. All of this information comes from the capability registers of the hardware. Now let's look at the output of an event ring, and there you see the controller has a primary interrupter and we have some information about the top about the interpreter itself, and here are the event TRBs, both that are completed and pending, and the pointer here shows you where the controller is in processing the event. Let's look at command ring. So the output is very similar. You can see all the list of command TRBs. The pointer shows you where the controller is actually processing the commands at this point. The bang XHCI register lets you examine all the register states. So I just showed you how to load the USB 3 debugger extension and run various commands to examine the the state of the controller driver and the hub driver on the system. So now that you have seen a demo on how to use the USB 3 extension commands, let's look at how to view the activities of USB 3 drivers. I'm going to assume that you are already familiar with WPP tracing because this technology has existed on Windows for almost a decade. There is a lot of documentation on this in MSDN. In order to parse WPP messages, you need TMF files. On Windows 8, using a new WPP capability, we have decided to leave the TMF information in the public PDB file, so you can easily collect debug traces from these drivers and view the activities. One challenge with WPP tracing is that in order to collect WPP trace messages, you have to enable the providers. Since system crash or driver issues can happen anytime, even during boot, and the user may not have enabled the WPP provider, we extended the WPP tracing macros to save important trace messages in a circular buffer local to the driver, irrespective of whether the WPP provider is enabled or not. So you can think of this as an always on WPP logger. There is another name for this feature, which is WPP recorder. To view the information from this local trace buffer, we have provided a new kernel debugger extension DLL called rcdr-kd.dll. This DLL allows you to retrieve the message from the buffer, parse them using the TMF information from a PDB file, and display that on the debugger window. So let me show you a demo of this. What you see on the screen is Windows kernel debugger, WinDBG running. I have loaded up a dump file from my test machine. It's memory.dump file. So the first thing I'm going to do is set the symbol path, which I've already done. So I'm just going to show you bang sim path. That's the symbol. That's where I have the symbol files. Then I'm going to load the rcdr debug kd.extension that I talked about. So f:/rcdr kd.dll. Then you run the bang help. This will show you all the commands that are supported by this debugger extension. Bang help usually shows the list of commands from the last debugger extension loaded in memory. So as you can see here, there's a long list of commands here. The one command that we're going to be using a lot, and the most useful to us for debugging is the rcdr log dump. The other commands basically lets you save the log file, set the TMF path and all that. We don't need all of those in most of the cases. So let's look at let me show you the output of rcdr log dump command, and then you provide the name of the driver. In this case, we are interested in knowing what was the controller driver USB xhci.sys was doing right before it crashed. So I'm going to say USB xhci.sys and enter, and now it you see a ton of trace messages on your screen. These are the messages that recorded in various logged buffers by the XHCI, and way at the top you can see the list of buffers the driver had created for recording messages. So I have a big device tree on my test machine. So there's a buffer created for every device. There's one for the command ring, there's one for the interrupt ring, and there's one for the whole of the driver. Now if you know where in which slot your device is plugged in, you can just run the command directly for that specific slot and find out what the controller driver was doing. So I'm going to dump the log of one particular device, and there you see there are some commands, the output you see from that buffer. This is what the driver was doing right before it crashed. So the interesting aspect of this command is it automatically extracts the TMF information from the symbol file and formats the WPP traces and shows the output in a human readable form. So let's do one more driver here. I'm going to find out what the hub driver was doing at the time of the crash. So I'm going to give the name of the driver, USB hub 3.sys, enter, and there you go. This is what was going on in the hub. Now these are traces useful to driver developers. So in order to really make sense of these traces, you have to have a domain knowledge. You have to know what a hub usually does, what a controller driver does. So knowing what having a deeper understanding of the specification, USB specification, and how the transfers are done will really help in understanding the trace messages that is displayed by these commands. So to recap, you can now debug host controller and device issues faster by examining the state and configuration information with the new kernel debugger extension. You can also view the WPP based debug trace messages from both kernel and user mode and learn the interaction between the software and hardware. But to learn more about other debugging tools available for USB 3, please watch the other part of this video series, and also please follow our blog for more in-depth articles on USB technology. Thank you for listening, and happy debugging.
Let's talk about USB tracing. My name is Philip Reese. I'm a developer on the Windows USB core team, and this is the third part in a series on USB debugging. So, in this talk, I'd like to tell you, well, what is USB event tracing, as well as, well, how is it different from what existed in Windows 7, and what tools do you use? How do you use them? By the time we're done, we will have taken a trace and analyzed it, and connected events between an application and the USB core stack. More on that later. Our tracing is the richest tool in Windows for recording USB driver and bus activity. USB event tracing is all about seeing what the USB controller driver and hub drivers are doing. These drivers enable all USB devices on the system. In the trace, you'll find errors encountered by the drivers, the transfers that went across the USB bus, including device enumeration transfers, other control transfers, and raw data. And you will see power state transitions of USB devices, and you'll be able to differentiate among all of the events which events have to do with a device of interest versus which events do not. You may be aware that in Windows 7 we shipped event tracing in the USB 2.0 drivers. Now we have complete USB 3.0 drivers in Windows 8. These are instrumented in a similar way, but you'll also find full USB bus data is available as an option in the tracing, and we've added support for activity IDs, which are used for correlating events. The way to record a USB ETW trace is very simple. You can even have customers do it. You start tracing using a simple command script, and then you reproduce whatever issue you're looking to diagnose, or just try plugging in a device if you don't have an issue to diagnose. Then simply stop tracing once you're done reproducing the issue. The hard part could be said to be analyzing the ETW trace. Fortunately, we have an advanced tool called Network Monitor, or NetMon. It's made by Microsoft and it's a free download. We've added USB parsers to this tool so that you can view the traces generated as I mentioned. Using our parsers, you'll be able to see the USB data, and you'll be able to arrange the view however you like with USB columns and USB specific filters. Now I've got a device issue, so let's dive right in, take a trace, and analyze what's wrong. Okay, suppose you sell a USB device or a USB device driver, and your customer reports that the device is disconnecting. Well, it sounds like it's disconnecting. Let's see what that looks like. I'm going to open up an app that unfortunately causes my USB device to disconnect repeatedly. Now, I'd like to see what's going on here. So I need to do this again, but this time with a USB trace. I've copied the command scripts to take a USB trace, and I'm just going to start it up and do exactly the same thing. I'll start up my app, and it's going to record the device. Well, it seems like it's disconnecting. I wonder if it's a software or a hardware thing. We'll find out very soon. Okay, now it's disconnected, so I'm going to stop the trace there before it gets too much extraneous data or repeated data in it. And let's analyze it. Fire up NetMon. Okay, so this is where you start in NetMon once you've downloaded the parsers and the application. And the only thing I've done is added a few columns here. We have some USB specific ones, which I'll explain later. What I've added is USB-D status, USB length, and USB device description. So let's get started. Now this trace has slightly over 1,000 events in it. I don't think I want to sit here and read all of them with you. It would take much too long. So one way I like to start reading a trace is to look for errors. So the way you do that is with a NetMon filter. And when you start typing property dot, it brings up a list of all the properties you can filter on. Which, by the way, are also all properties that you can create a column out of. So I'm going to start typing USB, and that gives me a list of all of the USB-related properties. The one I'd like to filter on is USB is error. I want to see, did the stack record any errors in this trace? So I've entered the filter. I can apply it. And I actually have to add equals 1. So there are 73 error events. It doesn't look too readable to me. And so I'm gonna step back. The device sounded like it was disconnecting. And I wasn't sure if it was a hardware or a software thing. What I do know is I didn't unplug it. But did the device unplug itself? Did the host controller somehow lose track of the device? Let's find out. So I'm going to search for a different property. USB is disconnect. This will show me every time that any USB device disconnected from the bus. Again, I need equals 1. So it actually happened about 5 times. that seems right. We probably heard around, or almost that many, device disconnection sounds. And so let's figure out why I disconnected the first time. So we only need to really look at events that happened before this one. Now that I've selected the first frame, I remove the filter. It remains selected, and I can see the events that were filtered out before that came before this event. So immediately before it is a control transfer. I can see this is a control transfer to the root hub, which still could be interesting because the root hub is the hub on which the device is connected. It is a get port status to the root hub. So that's what told me the device disconnected. That's fine. The previous one is also transferred to the root hub. This turns out to be an interrupt transfer. So again, doesn't have to do with why the device is disconnecting. It's just telling us that it did disconnect. Here's an event that represents a transfer to the USB device, the beginning of a transfer to the USB device. It is a get descriptor event requesting string descriptor at index 5. Why are we requesting the string descriptor at index 5? Well, I happen to know that this application enumerates USB devices, and we can tell more by checking out the pattern of previous transfers. Now, these transfers we see completing because it has a status of successful. 24 of 255 bytes were returned. We have the same view expanded. A request for string descriptor at index 4, and it completed. Let's see the data packets. Wireless USB is one of the strings on this device. So that's pretty interesting. I don't see why a request for a string descriptor would be connected with a device disconnecting. So let's see what happened in the other cases. So I'm going to reapply this filter. It's very easy because it's still here. And these two events are adjacent to each other. They're saying the same thing. Here's the next time the device disconnected. So I remove the filter. Let's look at what happened before that. Okay, we have the root hub transfers that we saw before, and a request for 255 bytes from the device. Interestingly, it's the exact same request that preceded the previous disconnect. And if we look at all of these disconnects, the device always disconnects immediately following a request for that string descriptor. Well, that's the problem. The device does not like that request. So we need to either change the application so it doesn't request that string descriptor, or fix the device so that it responds with a more conventional error. Okay, that's all for the initial Netmon demo. Here's what's wrong. An additional feature in USB ETW is that we log a lot of events with activity IDs that come from upper layers. This means that when you have different applications and different devices all communicating with the USB core stack, you can correlate your individual actions of an application to the corresponding events in the USB core stack. In this diagram, we've illustrated that the events emitted by the USB core stack can't easily be differentiated between the applications causing them. But with activity IDs, you can now figure out which events are related to application B, for example. The implementation of activity IDs is actually done in a 16-byte GUID, or globally unique identifier. This identifier is attached to each event, and so when your application emits an event, it will have a given activity ID. When an application sets its activity ID, not only do its events get assigned that activity ID, but also driver events that happen on the same thread also carry the same activity ID. Suppose your application is performing a file transfer over USB. Then if your application assigns an activity ID, the USB core stack can also log its events using the same activity ID, allowing you to view exactly the USB core stack events that resulted from your operation. To make this a little bit more clear, let's do a quick demo of a trace with activity IDs. And here's a quick demonstration of activity IDs. Now I've taken a trace with an application, actually a UMDF driver, and the USB core stack all providing events. And I'd just like to show you how it looks to find the events that are correlated between these all the components. So I named one of my providers UMDF DLL. I just want to grab any event with that. So here's a bunch of events at the end of the trace. These are actually the ones that are caused by the applications. But I want to separate out which ones got caused by this exe that's writing and which ones got caused by the exe that's reading. It's actually extremely simple in Netmon. You just right-click, find conversations, and here they are. Now all of these events have the same activity ID because we've implemented activity ID propagation in Windows 8, both in the kernel and in the USB drivers. What will help demonstrate this a little bit more clearly is the USB direction column, which I'll go ahead and add. So you see that all of these are out direction events. I'm going to go back to the main trace by selecting all traffic in the left-hand pane. It keeps the same frame selected. You can more clearly see here that there's a mixture of out and in events from the USB core stack. And to find the other conversation, I'll just look at the read, find conversations. Here's all the ins. And even better, say I just really want to know what's related to my application overall. If I have just a couple of operations coming from my application, what I can do is create a filter for it. So I already know which conversations are the ones I'm interested in. I can copy a filter of them to the clipboard, paste that as my filter. Now Netmon provides a very nice filtering language where you can combine all kinds of Boolean expressions, use parentheses, even write comments like C style. I'll copy the other one to the clipboard, paste it in here, and apply. I do have to select all traffic here. Now here's all the events caused by either of my applications. So here we have all of the events from either instance of my application and all the related USB core stack events. In wrapping up, I'd like to reiterate that taking ETW traces is really great when you don't have the device in your office. But it can be used in that situation too to get a more comprehensive view of what's going on in the drivers and on the bus. We've shown how to use Netmon and its USB parsers to analyze ETW traces, and we recommend that you try out adding ETW events to your own applications and drivers. Remember, if you use activity IDs, it can help a lot with USB debugging. For more on USB debugging, please check out the other presentations in this series, Part 1, the overview, and Part 2, kernel debugging. In addition, our team's blog is a great resource, including several blog posts on USB ETW. For more information on these topics, try these Bing searches. Thank you!